into a new equipment or a new device, and in this time we will do the current to pressure IP transducer. Transducers are usually designed to have a linear characteristic and negligible fast dynamic. It does not have a dynamic, so basically I can express the output input relationship as a gain because there is no dynamic. So we assume that the transducer transfer function merely consists of steady state gain KIP and P dash of T, the output over P dash of S is equal to KIB. If I want to represent that, I will start with the P dash T of S, which is the output, draw KIP, and then this is P dash of S, the input. And that's what we did. Next, the control valve. Again, the control valve can be treated as the measuring device. If it is dynamic, you have to express it as a first order transfer function. If it is static, it's just a gain. Control valves are usually designed so that the flow rate through the valve is nearly linear function of the signal to the valve actuator. A first order transfer function usually provides an adequate model for operation of an installed valve in the vicinity of a nominal steady state. So the output here is W-2 and the input is P-T and the analysis is KV over tau V S plus 1. Again, if tau V is much smaller than tau P, the process time constant, you can assume a static valve. And this is how it is represented by a block diagram. So now we express the process, we expressed the measuring device, we express the controller, and we express the transducer and valve in a block diagram. We can put all those block diagrams together to look something like this. So this is the overall block diagram with the associated input-output relationships. Now let us examine another. Let's analyze the input-output relationship of the whole loop, not just single component. So let me share my screen. Okay, so what we want to do now is we want the overall block diagram of that, or the transfer function of x over x set point. What is the overall transfer function? So how do we do that? Well, first we need to define some parameters. We need to define some variables, and then I'm going to do it step by step to show you how we can do this. So what are the main parameters that we need to define? We need to define the controlled variable, what we want to control. In this case, we call it Y as a general, but in our specific case, which is the mixing tank, it is X or X dash, basically, the output composition. We need to identify the manipulated variable. What is our manipulated variable? In this case, it is W-2. We need to define our disturbances. What are the things that disturb our control? In our case, it is X-1. We need to define the controller output. We can give it a name P, okay, which is a general name, which determine what is the output of the controller going to the valve. The error signal, we give it a name E, okay. The measured variable Ym, okay, which is in our case Xm or X-M. Now, why we are using generic nomenclature or symbols, because we just want this to be applied to any case, not just specific to the blending system. So we are redefining the variable rather than using the symbols in the example. We are using a general symbol, which then will give us a general equation which we can apply to any system. And then y is the y set point. And then y hat set point is the internal set point, which is the translated set point into the signal that the controller is working with. Yu is the change due to manipulated variable change. If you have seen here, you can see that there are two branches. One is due to the disturbances and one is due to the manipulated variable. One change coming to X due to the disturbance and one change coming to X due to the manipulated variable. So we call this branch U and we call this branch D. And we need to identify those two. U is the branch describing the change in the manipulated variable. D is the branch describing the change in the disturbances. GC is the controller transfer function. GV is the transfer function of the final control element. GB is the process transfer function, and GD is the disturbance transfer function, and GM is the transfer function for the sensor and transmitter. Now, having all this listed, we can now draw a general form, a general representation of the feedback control system and derive the equation for the feedback control system. So let's go to the blackboard, sorry, the whiteboard, and do that. So if I want, using these nomenclatures, if I want to draw, so basically I will start with the process, or better than the process, we can now just add G process, which represent the process transfer. G stands for process. The process transfer function, we have plus, this is YU, the change due to the change in manipulated variable. This is disturbances transfer function, and this is Y disturbances, and they both produce Y, the output. This is D, the disturbances change. This is U, the manipulated variable, which is represented by W2. Again, we are using general names to make it more general and applicable to any situation. Then I'll take the measuring device, GM, measuring device. This is Y, and this is YM. And then we have plus minus. I get KM, and this is Y hat set point, and this is Y set point. So I need to transfer Y set point to Y hat set point. Then I have my controller GC. This is the error. This is P. Okay. And then I'll have my final control element. We'll just exclude because later on you can add PI, but we'll IP. Sorry, we'll exclude it for now. Okay. And this is PT or just P. And this is G valve, and then G valve controls U. So that is the overall transfer function, as you can see it here. And I will be deriving the equation for that transfer function. I have to get an input-output relationship. Remember, there are two inputs. One is the D, and one is the Y set point. So I have to get Y in terms of Y set point and D. What is the relationship between Y? If I change D, how Y will change? If I change Y set point, how Y will change? Basically, getting the equation out of the block diagram is just the opposite of getting a block diagram out of the equation. So what I will do is I will go according to this relation. So I will start by saying Y here, Y is equal to, remember, when we moved from block diagram into from equation to block diagram, we go to the end and we take that one and we just write an arrow with a block diagram. So we do the opposite here. So Y equal to what? Y equal to arithmetic addition between two quantities, YD plus or yu plus yd. Okay, now what is yd? This is equation 1. What is yd? yd is defined as, this output here is defined as what? As gd times d. So it is gd times capital D. This is equation 2. Whereas yu is equal to gb times u. To gb times u. And this is equation 3. Now all what I need to do is substitute 3 and 2 in 1. Just substitute. So what I will have y equal to g b u plus g d d. And this is equation 4. Okay, can I simplify it further? Yes, because I have an equation for u. What is u? U is gv times p. gv pulse times signal coming from the controller. So, and this is equation 5. And I can substitute 5 in 4 and produce equation 6, which will be y equal to gb gv. I take u and replace its values. gb gv p plus gd d. This is equation 6. Is there further simplifying I can do? Yes, I can. How? Because I've got a term for p, which is gc times e. gc times e. So we have p is equal to gc times error. And this is equation 7. And I can substitute 7 in 6. And this will give me y equal to gb gc e plus gd d. Okay, now can I still continue? And this is equation what? 8. Can I still continue? Yes, I can. Why? Because I've got a term for e. I've got a term for e, which is basically e is equal to y hat set point minus ym. Okay, and this is equation 9. And also y hat set point is equal to km y set point. This is equation 10. So I can now substitute 10 and 9 in 8. And let me go here so that I have space. So here what we have now, y is equal to what? Is equal to gb gc. Okay, gb gc km, or gb gc. Let me just write it down. gb gc times km y set point minus ym, plus of course gd d. Okay, now I can open this bracket, and this is equation, how much did we reach? 10. I think this is equation 11. This is equation 11. Now y is equal to, open this bracket, gb gc km y set point minus GB, GB, GC, okay, YM plus GD, D. Okay. Now, can I stop here? Yes, this I stopped. Why? Because I've reached the end. There is nothing more after Y set point. Okay. And for D, I also stopped because there is nothing after D. However, for YM, there is. I can, and this is equation 12. I can now say that YM is equal to GM times Y. And this is equation 13. And I can now substitute 13 and 12. Okay, so if I do that, this will be equal to Y equal to GB, GV, GC, KM, Y set point, and then substitute here, minus GM, GB, GV, GC, let's put YM in the big at the end, GM, Y. So what I did, I replaced YM with GM, Y. And then finally plus GD, D. And this is equation 14. Can I stop now? Yes, you can. But there is further simplification. What is this further simplification? If you can see, this is Y and this is Y. So I can take this to the other side. So I can do now Y minus, so it will become plus GB, GV, GC, GM, Y equal to GB, GV, GC, KM, Y set point plus GD, D. Okay. Now, if we take Y as a common factor, we will have Y 1 plus GB, GV, GC, GM, and this is equal to GB, GV, GC, KM, Y set point plus GD, D. Now we can divide and get Y alone. So Y equal to GB, GV, GC, KM over 1 plus GB, GV, GC, GM, whole thing multiplied by Y set point plus GD over 1 plus GB, GV, GC, GM, and the whole thing is multiplied by D. And this is just basically the transfer function, the general transfer function of the closed loop. All what you need to do now is find those G, those transfer function, put them into the equation, simplify, and you will get the overall transfer function, which describes for you how Y will change as a result of Y set point and how Y will change as a result of D. Any question in this regard, in this derivation? I'm going to send this derivation to you, okay, to your file section so that you keep it with you. But any problem in comprehending, understanding this derivation? It's just basically following the loop and trying to simplify and substituting one substitution at a time. Any question? Okay, I still have 10 minutes. Let me just consider another example. So basically what we did is we generalized the transfer function as you have seen, okay, and we could work with this one or we could work with this one. It doesn't matter, but we generalized the transfer function and made it, I mean, both are identical, okay, because if you remember, in this case we took 1 over tau as a common factor, and in this case we just kept it. So they are both identical, but you can work with any of them and you can find that the same results is there. Okay, so we worked with this standard block diagram, okay, and in this there is a forward path and there is a feedback path. Okay, and we worked with both of them to obtain the transfer function. Okay, and this is a quick derivation written for you in the animation. Okay, I just do it for you here as well as in the animation to show you how it's done. Okay, now let us have some hypothetical situations where we analyze this equation here. What happened to this equation? The first hypothetical situation is disturbance change. Remember, those variables y set point and d are deviation variables, which mean deviation variable, they are difference from steady state, which mean that if they don't change, if these values, if the set point is not changed, they are basically zero because they are deviation variable. Only if they change, they become a number. So knowing that, let us consider a disturbance change. When we consider a disturbance change, we mean that the set point is not changed. The set point is kept constant, which means that nobody is changing the set point. It is kept constant. And as it is kept constant, the deviation variable will equal to zero. Why? Because we are not changing that value from steady state. So we have the equation y equal to GB, GC, Km over 1 plus GB, GC, GM times y set point plus GD over 1 plus GB, GC, GM times capital D. So what happened in this case? This has not changed, so this whole term goes to zero. So y is only affected by disturbance. It's not affected by set point change. So we can erase this part and we can just focus on this part. And that's what we will do in the next few slides. So this transfer function, long transfer function, has been reduced into this smaller transfer function. Both closed loop transfer function has the denominator 1 plus GC, GV, GB, GM as a denominator. It's a common denominator. Later on, you will know that this denominator will be used to determine the stability. The denominator is often written as GOL. Why it is called GOL? Because if you go to this loop here, if I open this junction, imagine that I open this junction here and I put it here. So this is GM and this is YM. Now, if you multiply all those GM, GB, GV, GC, if you multiply them, they will give you the denominator. So that's why they will call all this GB, GV, GC, GM. They call it G open loop. Why open loop? As if you have opened the loop, as if you have moved this to this side. Open loop. They call it G open loop. So it is called 1 plus G open loop. The term open loop transfer function or open loop system is used because GOL relates YM to Y set point if the feedback loop is open just before the comparator. If we open and make it straight line, you will get the whole thing as a straight line. At different points, the above derivations, we assume that D is equal to 0 or Y set point is equal to 0. That is, that one of the two input was constant. Suppose that D is not equal to 0 and Y set point is not equal to 0, as would be the case if the disturbances occur during a set point change. Applying the superposition principle for linear system theorem. Thus, the response to a simultaneous disturbance variable and set point change is merely the sum of the individual responses. So the output changes as equal to the sum of both changes if they occur at the same time. But usually we consider one and the other one is kept constant. For that reason, you will get one of those terms disappearing. Next, we have example 10.1. You have this feedback transfer loop, and you are supposed to obtain the transfer function y as a function of y set point, comma d1, comma d2. So can you do it? Challenge yourself. Go take that. The example is solved in your textbook, but I will solve it next time using the whiteboard. But before I do that next time, I would like you to attempt. أبيكم تجربون أنت وتشوفون how you can do it, okay? Because this will make understanding much easier for you. So please try this before coming into the next lecture and see if you can do it. Meanwhile, I think I'll stop here and continue next time from this example to explain for you how we can further, develop transfer functions from block diagrams. Do you have any questions before I proceed? I mean, before I end this lecture? And we will meet, inshallah, on Wednesday. Any questions? Okay, no questions. Okay, for the tutorial, unfortunately, I'm having a test today, so there will be no tutorial, but next week we'll start resuming the tutorials and solving some problems in Simulink. So this week will be no tutorial because also the other section, they had a test yesterday, so we didn't manage to give a lecture. So there, I will use the tutorial for the other section as a lecture to cover the same material as we covered with you. Until next time, thank you very much for joining me in this session. I hope this session was informative for you, and please stay safe. I'll see you inshallah on Wednesday.